Alright, so previously we talked about imaginary numbers. Imaginary numbers are basically, when we try to take the square root of a negative number, and obviously we can't, because we can't take the square root of a negative number, but that's what we call an imaginary number, when we try to take the square root of a negative number. So yesterday we looked at examples where we simplified those numbers, right? If I tried to take the square root of a negative number, for instance, like the square root of negative 9, I would separate the negative from the 9, call this I, because the square root of negative 1 we called I. You can see it's also a number right there. And of course, square root of 9 would have been 3, so we would have considered this 3I. Okay, so that's what we were dealing with yesterday, just basically separating the negative from the number and calling the negative I and simplifying the number as we normally would simplify it. Okay. But now we're going to work our way towards complex numbers. And complex numbers, as you can see here, are written in the form A plus BI. A is going to be considered a real number part, and BI is considered the imaginary number part. Clear this off. Alright. So a complex number, it is called complex for a reason, I suppose, is actually consistent of two parts, a real part and an imaginary part. I is just the imaginary number itself, but the B is the imaginary part of the number, and A is the real part of the number. Alright, and it is kind of weird because this is considered to be one number, but it's kind of strange to us because it's one number that really looks like a binomial. It has two parts. This is the only kind of number you will ever work with that actually has two parts, but this is considered one number. This is considered to be a complex number. So the name does not deceive you. It is sort of complex in that way. It's got two parts to it. But we consider the A part the real part. We consider the B that's associated with I. We're going to call that the imaginary part. You can see some examples up here in this box. Real numbers are things that you've seen before, negative 1/2, 0, 1.73, square root of 2, pi, all those things. Those are real numbers. Every number you've probably dealt with up to this point in your career in high school is real numbers, essentially. Imaginary numbers, we introduced those yesterday, is basically anything that has the I on it, or, of course, the square root of negatives, because that's where the I comes from when you try to do the square root of negative numbers. Alright, and of course up here you can see these are complex numbers. Again, these are considered to be one number. So 3 plus 7i, we consider that to be one number. 3 is the real part, and the 7 is the imaginary part. Here's another complex number. 3 would be considered its real part, and 2/3 would be considered its imaginary part. And another complex number, 4 would be the real part, and then I guess negative 1 would be considered the imaginary part. Alright, so that's kind of important to remember or emphasize the fact that these complex numbers are consistent of two pieces, a real part and an imaginary part. And this in bold here kind of explains everything we need to know about what we're going to do in our next couple problems. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So essentially, if I have two complex numbers, let me just say like 4 plus 3i, and well, we're going to have variables in here essentially. Let me call that, well, we'll call it 4 plus 3i. And the only way I can have another complex number equivalent to it is if it's exactly the same. It's also 4 plus 3i. But the problem that we're going to run into in these examples is we're going to throw x's and y's in here. And we're going to have to find the value of those x's and y's to make these equal. So for instance, I could have the complex number 4x plus 3i, and I can have the number 8 plus maybe 6yi. And these two numbers would only be equivalent if the 4x is equal to the 8, and if the 3 is equal to the 6y. And that's essentially what we'll do, is we'll set these up equal to each other, and we'll find the x value that would, of course, or x and y value that would make them work, that would make them fit. So that's the goal of our next couple of examples, is we're going to solve for x and y that would equal our complex numbers. I'm going to I guess I'll let this one kind of play out. Because this one does give us fractions, and I don't like starting with fractions, but let's go ahead and take a peek at it anyway. The point is basically how to solve it. So find the values of x and y that make the equation 4x plus 10i equal to 2 minus 4yi. So this is a complex number, and we're saying it's equal to this complex number. So that means the real parts must be equal to each other. And you can see here the real parts emphasized are the 4x is a real part and the 2 is a real part. So they must be equal to each other. 4x would equal 2. And the imaginary parts would have to equal to each other. So our imaginary part, I have 10 and I have 4y. But you got to be careful because that's a minus right there. So that's going to be considered to be negative 4y. So that would mean 10 would have to equal negative 4y. And we would solve those two equations, we would solve them for x. Right? For solving this one, I would divide this by 4 to get the x by itself, and I would have x equal to 2 over 4, which is equivalent to 1/2. Right? You can reduce these by 2, and you'd have 1 over 2 or 1/2. For the imaginary parts, we'll divide by negative 4 to cancel that out, leave you with y. When I do it to this side, though, 10 divided by negative 4, I can reduce this. I can again reduce these by 2, which would make this 5 over 2, so negative 5/2. So that would be the x and the y there. I'm going to erase it because it's going to be on the slide anyway. But equate the real parts together and equate the imaginary parts together. So just to kind of go back over this problem, you see here they obviously outlined these are the real parts. 4x plus 4x and 2, so they set them equal to each other. And they emphasize the imaginary parts, the 10i and the negative 4y, I. But you don't really put the i's in here, you just sort of, it's just the b portion of it. 10 and the negative 4y. The I is just there so it helps you identify which part of this is imaginary, but the 10 is the part that we're going to equate to the negative 4y. So put those equal to each other and solve. So that's what we've done. So let's try another one, kind of similar to it. Find the values of x and y that make each equation true. So this is our first example, I guess. So again, identify the real parts. Again, these are only true if the real parts are equal to each other and the imaginary parts are equal to each other. So, identify your real parts. So for the first complex number over here, the real part is the 2x. And for the second complex number, this one over here, the real part is the negative 8. So that must mean the 2x should equal negative 8. And we'll solve that equation in a minute. But let's go ahead and identify my imaginary parts. So for the first complex number, the imaginary part is negative 6. Be very careful, make sure if it's a minus sign, you remember that that is considered to be negative 6. And for the second complex number, I have a positive 20y. So that must mean negative 6 would equal 20y. Right? And we solve these for x and y. So if I solve this for x, I can divide by 2, and x would equal negative 4. For the y's, if I divide by 20, which is a kind of a weird fraction, but it'll work. I think I can reduce these by 2, which would make it negative 3 over 10. And so I've solved for x and y. So basically, it's really weird looking and really random looking, but remember the one thing we pointed out earlier here with this star. Okay, the two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So again, all we're really doing is setting the real parts equal to each other and the imaginary parts equal to each other and solving for their x's and y's respectively. So let me clear my screen off and you can see that they've done it the same. Okay? And equate their imaginary parts. Alright? So, complex conjugate, that's the next thing to point out or emphasize. And this really isn't that difficult, or it's not complicated at all, because all we're essentially doing is changing a plus to a minus. However, you got to make sure you're changing the correct plus to the minus sign, or vice versa. Because if you do it in the wrong place, then it's going to not be right. So that's the main thing. Just make sure you know what you're supposed to change, but changing it is easy. Because all we're doing is essentially changing a positive to a negative, or change a negative to a positive. So a complex conjugate, here's an example of it. Negative 5 plus I squared root of 10, its complex conjugate is negative 5 minus I squared root of 10. Or basically, all you do is change the plus to a minus. Okay? That's what a complex conjugate is. You can see here. The complex conjugate of any complex number, a plus bi, is the complex number a minus bi. So again, all essentially is happening is we're changing the plus to a minus. However, it's for the imaginary part. We're not changing the a's sign, right? A is still positive. We're just changing the imaginary part's sign. So that's going to be very important, because sometimes these problems are written like this, where the imaginary part is written first and then the real part is written second. And a lot of times people just go, oh, you know what, I just need to change my plus to minus. But that's actually incorrect if it's written this way, because you're not changing the sign of the imaginary part, which is essentially what you should be doing. When you just change the sign of the real number part, that's not a complex conjugate. So that's what we got to be careful of. Okay, so let me do one or two of these examples and sort of emphasize that a little more. So find each complex conjugate. So what I personally prefer to do is make sure, step number one, that every single complex number is written with a plus or minus bi. But have the a, the real number, written first, and then the imaginary number written second. So here in this example, example A, 8 plus 5i, I've already have it set up. The real number is written first, and the imaginary number is written second. So if that's the case, then all you got to do is change your sign. So the complex conjugate of 8 plus 5i is simply 8 minus 5i. And that's it. Alright, so for part B, it's a little different. I still want to make sure I write this in this format, a plus bi, or a minus bi, depending. But what would a be here? Well, if you don't see it, that must mean this is the same as a being 0. So really this number is 0 plus 6i. So that's kind of important to note, because you want to make sure, again, that you're changing the sign correctly. So if I were to change this complex conjugate, it would be 0 minus 6i, or essentially a negative 6i. I do apologize for making this seem a little more complicated, but I'm trying to make sure you don't make a mistake. And when I get to an example where 9 out of 10 people make a mistake, I'll emphasize why that's, again, so important. But you can see they've done it the same way that I've done it. Alright, these problems right here, A and B especially, are ones people would get wrong a lot of the time. Or not A, I guess, but B particularly. Let's start with B to emphasize my point. Okay? The complex conjugate. So many people would write I minus square root of 3. However, that is not the correct complex conjugate. That is not the complex conjugate. That is wrong. And the reason is because this number is not written with the real number portion first and then the imaginary number second. So really, you should write this as square root of 3 plus I. Not I plus the square root of 3. Okay, write the real number first and then the imaginary number second, and then just change the sign. So square root of 3 minus I. That's the complex conjugate. And why is that different than I minus the square root of 3? Well, is 2 minus 4 the same as 4 minus 2? No, it's not. So it does matter which term is written first. Again, another sort of tip that you really just need to know is essentially all you're doing is changing the sign for the imaginary part. Not the real number part, just the imaginary number part. So here it was a positive I, but of course we would change it to a negative I, essentially is what it comes down to. That's pretty much all you're doing. But my advice of rearranging it into this form, I'm only giving you that advice to help remind you or hopefully prevent you from making any mistakes. Okay? So let's go over to A. A is 9 minus I. That's already written with A plus BI form. Basically the real number first and the imaginary number second. So again, all we're essentially doing is changing the sign of the imaginary part. Really the complex conjugate here is just 9 plus I. And for C, again, we're just changing the sign of the imaginary part. So the imaginary is negative 8. So we're changing the sign, it would be a positive 8i. Okay? Of course, if you set it up like we set it up in the previous problem, I think on the last slide, I would have told you to write it as 0 minus 8i. Of course, you change it from plus to minus. And it's the same thing, it's still positive 8i. So you have two ways you can think of it. I don't care which way you think of, okay? Either always set it up like this and just change your sign, okay, and you're good. Or just basically think of this, changing the sign for the imaginary part. They're both the same thing. I don't care which way you remember best, but as long as you can remember it. They're exactly the same. I just don't know how your mind works, so you can kind of make your determination on that. All right. So here, and this will be the last problem I think I do for this. Ignore this. There's a couple ways we can solve this, but my preferred way, to find the zeros of the function, I'm going to be doing just the quadratic formula. Okay? The quadratic formula will help me find the zeros of a function. That's what it's meant to do. And if you don't remember, this is my quadratic formula. B, negative b plus minus square root of b squared minus 4ac, all divided by 2 times a. So, we'll identify a, b, and c. A here is 1, because it's 1x squared. B is 10, and c is 26. So let's plug it in our formula, and let's start solving for these zeros. So, negative b would be a negative 10, plus or minus square root. B squared, that's 10 squared, minus 4 times a is 1, times c is 26. So if we put all this here, or it's still over 2 times a, 2 times 1, oops, which will just be 2, but let's just go ahead and plug it in first, and then we'll simplify. So if I simplify, I still have negative 10 plus and minus, but let's focus our attention on the inside of the square root. 10 squared is 100. And 4 times 1 times 26, so 4 times 26 is 104, so minus 104, all divided by 2. So again, if I keep simplifying the inside of the square root, it's negative 10 plus minus 100 minus 104. 100 minus 104 is negative 4 over 2 still. Alright, so now we come to the issue where we have the square root of the negative. That's the imaginary thing that we're going to have to fix. So let me go ahead and do that over here, kind of some side work. So the square root of negative 4. Remember, always separate the negative from the number. So I'm going to separate the negative from 4. The square root of negative 1, we're going to call this I. And the square root of 4 is 2. So this is going to be 2i, basically. So let's go ahead and change it over here. Let me continue this way. So I have negative 10 plus minus 2i over 2. Alright, so I'm pretty much done, but I could simplify this. Remember, you can write this as negative 10 over 2 plus minus 2i over 2. So essentially separating this 2 into both of these. Negative 10 over 2 is negative 5, plus or minus 2 over 2 is 1, so 1i essentially. So our answer here would be negative 5 plus and minus I. And again, that is our complex number. It has a real part, which is the negative 5. People hate my 5s. And the imaginary number part, which is 1i. And we have both complex conjugate in this as well, because we still have the plus and minus that's part of the equation. So really, you could write it if you really wanted to, negative 5 plus I and negative 5 minus I. But writing it as negative 5 plus minus I, essentially writing both of these in one. So leave that as your answer and you're done. So follow the quadratic formula, put these things together. You guys can do, plug numbers in and then start mapping it out. Just once you get to this portion here, where you take the square root of a negative, make sure you simplify that in terms of I, and then just, continue simplifying your problem. All right. You guys can probably stop watching the video here if you think you have the point. I'm going to just go one more here, one more problem, just so you guys maybe can work with me if you want to, and hopefully see if you can kind of get the grasp of it. Okay? So you're welcome to pause this and try this problem, and then see if you got it right. So here, same idea. I'm going to do the quadratic formula. Plug everything in and then evaluate. So let's identify A is 1 here, because it's 1x squared. B is negative 8. Very careful, make sure you understand that that's a negative. And C is 18. So if I plug everything in, I have negative B, which B is negative 8. So that would be a positive 8. Because a negative 8 would be a positive 8. Plus minus the square root. B squared. So it's going to be negative 8 squared. And again, if you're putting that in your calculator, please use parentheses. Minus 4 times A, which is 1, times C, which is 18. All divided by 2 times A, which is 1. So if I start simplifying, let me focus my attention on the inside of the square root. Negative 8 squared is a positive 64, minus 4 times 1 times 18. So 4 times 18, 72. So minus 72, all divided by 2. Again, so 64 minus 72, let's go ahead and simplify this in there. 64 minus 72 is negative 8 over 2 here. Alright, so again I have the square root of negative numbers, so let me go ahead and simplify that over here. The square root of negative 8. Separate the negative from the 8. So this is I. And 8, I can simplify that. I can break it into 4 and 2, because 4 is a perfect square. So this would become I, square root of 4 is 2, the square root of 2 remains as left over. So really it's going to be 2I square root of 2. So let's go ahead and write that back over here. 8 plus or minus 2I square root of 2. Remember I just said square root of negative 8 is the same as 2I square root of 2. So that's what I've changed here. This to the 2I square root of 2. Still over 2. And see if you can simplify more. Go ahead and separate these parts. 8 over 2 plus minus 2I square root of 2 over 2. 8 over 2 is 4. And we're focused here because these 2's are both outside the radical. I can't really do anything with the 2 that's on the inside of the radical because it's inside the radical. I can't really mess with it. But these 2's that are on the outside of the radical, they cancel each other out. And so that should just leave me with I square root of 2 as my final answer. So that one had a couple tricks to it, especially the negative here. Making sure that this double negative turns into a positive, and that when you square this, you end up with a positive 64. So that B value being negative, those are a couple potential points of mistakes. Another one would have been, of course, the square root of negative 8. You may have simplified that incorrectly. Hopefully you didn't. But that would have been another issue or another point of concern. And then the last part where a lot of people would probably make mistakes is when they separate this 2, they divide it into 8 and they divide it into that 2 as well. But I hope it makes sense. Hope it all works out. Hope you understand the answer where it comes from. Follow the quadratic formula. Don't make any of those mistakes that I've kind of pointed out. And good luck to you guys. Good luck. If you're still needing help, please come to tutoring, come ask me for help during my time, whatever the case is. I'll be happy to help you. All right. See you later.